Exercise 1.18. A point charge plus 10 microcoulomb is a distance 5 cm directly above the center of a square of side 10 cm as shown in the figure. What is the magnitude of the electric flux through the square? Here in the figure, a square is given where the side of the square is 10 cm. Now we will find the magnitude of electric flux through the square. So this square can be considered as one face of a cube of edge 10 cm with a center where charge Q is placed. So that cube encloses the charge Q, and this cube is considered as a Gaussian surface where the square in the figure is one side of the cube. Now according to Gauss theorem, for a cube or for a Gaussian surface, the total electric flux will be equal to Q divided by epsilon 0, where Q is the charge enclosed by the cube. So here the cube has 6 phases. So the total electric flux through all its 6 phases is Q divided by epsilon 0. Hence, the electric flux through one phase can be written as 5 divided by 6, because a cube has 6 phases. Total electric flux is Q divided by epsilon 0. So flux through one phase is 5 divided by 1 by 6, which is equal to 1 by 6 into Q divided by epsilon 0. This is the flux through one phase or flux through the square, where epsilon 0 is the permittivity. Value of epsilon 0 is equal to 8.854 into 10 raised to minus 12 Newton raised to minus 1 Coulomb square meter raised to minus 2. The value of Q is given in the question. It is 10 microcoulomb. Convert it into coulomb. So it is 10 into 10 raised to minus 6 coulomb. Therefore, the flux through one phase or flux through the square phi is equal to 1 by 6 into Q divided by epsilon 0. Instead of Q, we can substitute 10 into 10 raised to minus 6. Instead of epsilon 0, it is 8.854 into 10 raised to minus 12. Simplifying this, we will be getting the answer as 1.88 into 10 raised to 5 Newton meter square Coulomb raised to minus 1. This is the electric flux through the square. The electric flux through the square is equal to 1.88 into 10 raised to 5 Newton meter square Coulomb raised to minus 1. Exercise 1.30. Obtain the formula for electric field due to a long thin wire of uniform linear charge density lambda without using Gauss law. So here we have to find the electric field without using Gauss law. So we will apply Coulomb's law. So in order to solve this, here we will consider a long thin wire XY with a linear charge density lambda. Lambda is the linear charge density. Now consider a point A at a perpendicular distance L from the midpoint of the wire. So here I am considering a point A at a perpendicular distance L from the midpoint of the wire. Now here I am joining A to another point on the wire, that is Z, where OZ is given as X. Let this angle be theta. Since AO is perpendicular, this angle is 90 degree. Now let E be the electric field at A due to the wire XY. Now we are considering a small length element dx in the section OZ. So here we are considering a small length element dx. Let Q be the charge on the wire or charge on OZ. Therefore, I can write Q is equal to lambda dx, where lambda is the linear charge density. Now, according to Coulomb's law, electric field is 1 by 4 pi epsilon 0 charge divided by the distance square. So here the charge is Q. Instead of Q, we can write it as lambda dx, and the distance is AZ. Distance between the point Z and A is AZ. So I can write this as AZ the whole square. This is equal to 1 by 4 pi epsilon 0 lambda dx divided by A is at is the hypotenuse of the triangle AOZ. Therefore, AZ can be written as root of altitude square plus base square. So it is L square plus X square. So instead of AZ the whole square, we can write it as L square plus X square. So we got an equation for the electric field DE. DE is equal to 1 by 4 pi epsilon 0 lambda dx divided by L square plus X square. Here, the electric field is resolved into two rectangular components. DE cos theta is the perpendicular component and DE sin theta is the parallel component. When the whole wire is considered, the component DE sin theta is cancelled. Only perpendicular component DE cos theta affects the point A. Here, the effective electric field at point A due to the element dx is due to the perpendicular component of the electric field. Therefore, I can write DE or perpendicular component is equal to lambda dx cos theta divided by 4 pi epsilon 0 x square plus L square. Now we will consider the triangle AZO. Triangle AZO. We will find the tangent of the angle theta, tan theta. Tan theta is opposite side divided by adjacent side. So tan theta is equal to x divided by L. From this equation, we can write x is equal to L tan theta. Differentiating both sides, dx by d theta is equal to L sec square theta, or dx is equal to L sec square theta d theta. So here we got an equation for dx. Now, we know that, or I am writing x square plus L square as L square plus, instead of x I can write L tan theta. Instead of x square I can write it as L square tan square theta. Where L square is common, take L square outside. So L square into 1 plus tan square theta. Where 1 plus tan square theta can be written as L square sec square theta. So here we got an equation for L square plus x square in this equation. Now substituting all this equation in DE. DE is equal to 1 by 4 pi epsilon 0 lambda. Instead of dx we can write it as L sec square theta cos theta d theta divided by, instead of x square plus L square we can write it as L square sec square theta, where sec square theta cancels and L also cancels. So here the equation DE becomes lambda cos theta d theta divided by 4 pi epsilon 0 L. So we got an equation for DE, lambda cos theta d theta divided by 4 pi epsilon 0 L. The wire is so long that theta tends from minus pi by 2 to plus pi by 2. So this equation can be integrated within the limit minus pi by 2 to plus pi by 2. So integral DE minus pi by 2 to plus pi by 2 is equal to integral of lambda by 4 pi epsilon 0 L cos theta d theta within the limits minus pi by 2 to plus pi by 2, where lambda by 4 pi epsilon 0 L is a constant. So lambda by 4 pi epsilon 0 L. Integral over cos theta d theta is nothing but sin theta. Applying the limit minus pi by 2 to plus pi by 2. Sin pi by 2 minus sin minus pi by 2, that is 1 plus 1. So the equation becomes lambda by 4 pi epsilon 0 L into 2. Here 2 cancels. So we got the equation for electric field lambda divided by 2 pi epsilon 0 L. This is the equation for electric field due to a long thin wire of uniform linear charge density lambda using Coulomb's law.